Hello, welcome to the Points of Topology Lab Session 11. This is Shovik, working on Reynolds costume and mattress. So before starting, let me know whether I'm audible and is the screen visible to you or not. Please, anybody to confirm, Mr. Mustaq? Can you please confirm whether I'm audible and is the screen visible
Visible,
to you?
visible and audible.
Okay, thank you for the confirmation. So before starting, okay, there will be last three consecutive session. One is this today, and another will be tomorrow. That will be 1 hour session, and last session will be on this Sunday. That will be 2 hour session. Okay, so we have only three sessions left. Okay, so so as you know, the spirit of this of these live sessions are mainly the problem solving. So if you have any doubt or any question regarding the previous sessions or anything you want to ask for assignment, please let me know. Do you have any question from previous sessions, or do you have any doubt from assignments, or and do you want to make any concept clear, anything like that? Do you have? If yes, then please ask me. Okay, okay. So in case you have any doubt, you can always stop me in the mid of the session and ask. Okay. So, okay, so today we shall start with assignment 9. Okay, so let's start. 1 minute, please. Okay, so today we shall start with the assignment 9. Okay, so the first question is as follows. Okay, so first I shall start with the true false type of question. Okay, so first question is that if topological space X is separable, then every collection of disjoint open subsets of X is countable. So this is true or false? This is true or false? So what is the question asked for? The question is asking that 1 minute. Okay. So the question is asking that if there is a topological space X which is separable, then every collection with disjoint open set of X is countable. So for a separable space, is it possible to have uncountable disjoint collection of open subset of X? So okay, so okay, so try to think how to approach this problem. Okay, so let me tell you firstly. Okay, so the it is quite difficult to guess the answer, right? It is quite difficult to guess. So let me tell you the answer. The correct answer is true only. Okay. Now try to prove. Now try to guess or try to figure out why it is true. It has to be true. Okay. Are you understanding? So the question is that X is given topological space and every collection of disjoint which is separable. Now we need to prove that every collection of disjoint open set of X is countable. And it is already known to be true. Okay. So now try to show that why this is the case. So how you can approach, so let me give you a hint. So so you you can use the method of contradiction. Okay. Use method of contradiction. So then you will. then you can solve it. Okay, so please try to do it by yourself and let me know. Okay, I shall be wait for a few minutes. So so start with the method of contradiction. So assume that there exists a collection of opens which is not which is uncountable. Now try to figure out some kind of contradiction. Okay, take your time, think about it, and let me know. Okay. In the meantime, let me find out some other questions. So yeah, so please try it yourself first. If you're able to solve, Mr. Mustaq, then please let me know. And also if you're unable to solve, then also please let me know. Then I can explain it to you. And in the meantime, if you have any doubt or you want me to explain something more than one time, please don't hesitate to ask. Just stop me and ask. Okay, these sessions are mainly for problem solving, understanding, clearing doubts, understanding concepts for these things. So please try to make use of these sessions. Okay, please try to solve it right now. I shall be after a few minutes. Okay. Okay. So are you able to solve it, Mr. Mustaq?
First of all,
Yeah.
X is separable topological space, means
Okay.
there exists a countable tensor subset.
Correct.
So consider any collection of disjoint open subset in X. So we have to show actually I must any set in X is countable. So
Correct.
first of all, we take just by we want to prove this by contradiction. So the set is I.
Okay. Wait.
I
Let me write it down. So you choose the set to be I, right? So call it U to be the collection of disjoint open sets. 1 minute. Okay. Then U to be the collection of disjoint open sets. Then
subset and
uh, then
the UI actually UI index.
Okay. So basically, these are all UIs. Okay, then
So first of all, we want to prove this by contradiction.
correct.
So key main idea is that I suppose I take let I where I is uncountable.
Okay, let I be uncountable. Okay, then
Since each
hmm,
since each UI is open and disjoint, they are pairwise disjoint.
correct.
So we can write U as the union of I index I U, which is an open set. The U is also an open set because union of all open set is open.
So that union of UI, this is also open. Correct. Okay, right. Then
Since D is dense in X,
okay, so X separable.
X separable,
So let
D
D be the
we take
countable.
a dense subset countable dense subset D earlier.
One minute, let me write down. So D be the countable then subset. Okay, then
So D intersection U is dense in U.
U.
At
So U means you are saying that union of UI you are calling to D, right?
D intersection U is dense in U.
No, here U by U you are saying U is nothing but the union of UIs, right?
D intersection U.
Okay, one minute. So D D intersection U. This is what this is. D intersection U. This one
Also dense set.
also dense, correct? Okay, then
Then if I is, however, if I is uncountable,
okay.
U would be large union of disjoint open set.
What does it? What does by? So what? So what do you mean by large union? What do you mean by large
I
union?
because I is uncountable, you must be large not actually large not is a infinite union of
Uncountable. You mean saying uncountable?
uncountable.
Okay. Okay. Then
Then it would be difficult to be a fit a dense subcountable sunset D into U. So it is
so it would be not possible. It is not possible to do what? To do.
it will not be possible
Hmm.
the fit a dense countable subset D into U.
Correct.
So it's contradiction.
One
Actually, especially without D, it's countable.
minute.
Then we would have too many disjoint covered with D, so it is countable cover.
Absolutely correct. Very good. So basically, let me explain. Okay, so whatever you told, Mr. Your argument is absolutely correct. Okay. So let me re-explain this for the other audiences because that has to be uploaded in the YouTube also. Okay. So what Mustaq has explained is the following. Okay, in the so I am re-explaining your argument. If I am making any mistake, please rectify me. Okay. So so start with what? Start with and start with collection. Start with some UIs. Okay. Now we need to show this collection is countable collection. Okay. So now, mm, so let's assume it is uncountable collection. Okay, let's assume it's uncountable collection. Okay. So now what we are doing is the following. So it is uncountable collection. So now since D is countable dense, this is the D, it's a countable plus dense. Why? Because X is separable. So such a situation is always possible. Okay. So D intersection Uy non-empty for all I. Okay. But these collect, but there are, but so these are uncountable. There are uncountable EYs, correct? So this tells what? This tells that, so this tells D contains uncountably many points of UIs for each I. So yeah, so and that is not possible. Why? Because D is countable. Not possible since D is countable only. Okay. So this is the argument. So yeah, so that's all. Okay, so Mustafa, whatever you said is absolutely correct. So this is what you what I've explained just within few seconds. This is what you argue, correct? Am I audible?
Yes, yes.
Okay, so whatever the argument you gave, and this is the gist of the argument. Am I right? Or is there any mistake?
That's fine.
Okay. Okay, thank you for the confirmation. Okay, so now let's go for the next question. So the next question is as follows, the 1 minute. The set of integers z equipped with the cofinite topology is not semi-countable. So the set of integers z with cofinite topology is not semi-countable. Okay. So it's a true false question. Please first think and let me know what, so it is true or false, and whatever you think, please give an argument for that. Okay. So we have only the set of integers with the cofinite topology, and we need to find out whether it's second countable or not. Okay. Second countable means what? Second countable means what? It has a countable basis for its topology. That is must have a countable basis for its topology. Okay. So now try to, so this is the definition. Now try to figure out the whether such a situation is possible or not. Okay. Please take your time and let me know. Okay, are you able to figure out how to approach this problem, or do you have an idea how to start this? Okay, okay. Let me tell you one thing very much clearly. Please don't look at the solutions manual. Please try to figure it out by yourself. Okay, that's if you're unable to solve, no problem. Please tell me. I will explain. Okay. So now tell, are you able to figure out till now how to
I
approach or
think it is true also because
yeah, tell me.
Z with co-finite topology cannot have a countable base.
Okay, so according to you, it should be true, you are saying, right?
Yes.
Okay, what is the argument?
It is not that much solved because any open set in the co-finite topology is either
Okay,
Z or has a finite complement.
uh, okay. Uh, but so what I was saying is that any cofinite, any fine. Sorry, can you please repeat the argument? I'm unable to. Can you please repeat the argument?
No, the voice.
Huh,
Okay,
can
I just repeat
yeah, yeah.
that
Can
because
you?
the consider actually when we in cofinite topology on
Okay.
J, the open sets are all subset of J whose
Yes.
complement are finite along with the open set, empty set.
Okay.
The open
Huh.
there is the open set is phi Z
Hmm.
itself and any open subset of Z whose complement is finite.
Any open subset of Z. Any open set of
Any
Z.
subset of J whose
Ah,
complement is finite will be is open set.
okay. That's okay. That is by definition of the cofinite topology, right? But from this, how we can conclude that it cannot be second countable? Because for second countability, what we need? We only need the that set should have a countable basis for this topology. So, so how you can tell that it should be
From
it has
that
to be the case?
actually from the basic
Uh,
actually any open set in the cofinite topology is either Z or has a finite complement from the basic condition actually or
correct. From
definition.
the definition, yes, correct.
This means that every infinite subset of Z, its
Yes,
complement is finite or subsets are open.
correct.
So from there we can say that there are uncountably many subset of Z with finite complements is open.
There. So you're saying there are uncountably many subsets of Z.
Subsets of Z with finite complements
Uh,
each.
how that? How it is uncountably many subsets? Because the number of elements of Z has only countable elements, right? So can you explain how you can say that it has can have uncountable number of subsets?
Because Z has many countably many subsets.
Correct.
So just to consider a finite subset, a subset of Z,
Correct.
the set Z complement A is open.
Correct.
So there are uncountably many finite subset of Z.
Well,
Consider the
so
B.
okay, so I understand the problem in the argument. So according to you, let me write it down what you explained. So let yeah, if any mistake, let me correct me. Okay. So according to you, there are uncountably many open subsets of set, right? So this is according to you. Am I right? Am I right?
Yes. Yes, yes.
Okay, but but this is wrong. Okay, so let me explain. So so the number of open subsets, the number of open subsets of Z are in bijection with number of finite subsets of Z. Correct? Is it correct? The number of open subsets of Z are in bijection with number of finite subsets of Z itself. Am I right?
Yes,
Okay, this is because the open set complementary finite. Okay. Now, in Z, how many number of finite subsets of I mean in Z, how many finite subset is possible?
uncountable.
No. So finite subset, how many you can take? So finite subset can have call it F. Okay. So call a finite subset of F. So suppose F has only one element. So how many such a F is possible? Countable times, right? Now suppose number of element of F is 2. Then then how many F is possible? That is from the countable that is from countable collection. How many ways you can choose to distinct numbers? That is what. So this is some call it xi. Then I mean xi C2, which also countable, right? I mean, forget about Xi. The point is that from a countable set, you can only choose. I mean, so since Z is countable, so and suppose there is a finite set with certain number of elements, call it n. Okay. So from a countable set, how many way you can choose a finite set having the number of elements n? It will be countable only, right? Correct. So similarly, if number of element of f is n, so how many ways you can choose f xi cn? That is also countable, correct? So this tells what number of finite subset of z is countable only. How do you understand?
Yes, yes.
This tells that what? This tells that there are countably many open subsets of x. Countable many open subsets of Z. Okay. So second counter. Is it clear to you? Stuck?
Yes, I understand.
Okay, thank you. So see, so I mean, what you observed is that there is something which seems to be quite obvious, but if you use some kind of countable argument, then that obvious thing seems to be incorrect. Okay, so that is the problem, and that is the beauty of the subject topology. Okay, so that's why practicing. That's why I think you should practice more and more. That otherwise the catching this type of situation will be a tricky. And anyway, practice will give you good marks in exam also. That is also important. Okay. So now let me write in the next question. Okay. Let A be a non-empty subset of R with usual topology. And let there exist two continuous functions f comma g to a such that if A union GA is equal to A. And if A intersection GA is equal to empty, then A cannot be equal to 1 millimeter down R 0 1 close 0 open 1. So uh, so 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 let me read out the question first. Okay. So A be a non-empty subset of R with usual topology. Okay. And suppose there is a continuous function f and g from on capital A itself such that the union is capital and the intersection is empty. Now question is A cannot be which of the options, that is under which of the, that is which of the either R or closed J1 or closed open one, which of this thing cannot admit such two continuous functions satisfying those two properties. Okay. So yeah. So so try to figure out how, which of the, or first try to figure out the given condition, this given condition, what this will imply. So first you need to figure this out. The given condition, what this will imply. Then only you will understand how this I mean then only you will understand which of the following option cannot satisfy the given the existence of such function and satisfying those two properties. Okay. Are you understanding the question? Okay, I hope you understand the question. So okay, so try to think about it. Let me know which one is not possible. Okay. So so the okay, so the hint is as follows. I mean, anyway, it is not a MCQ question, so that's why I need to give a hint also. Okay, 1 minute. The hint is uh first try to guess given conditions are related to something. It is not random, it is something very familiar. What is that? What is that? Okay. So try to think and try to figure out and let me know. Okay. If you are unable to understand the question, please ask me. Or if you understand the question clearly, then please try to figure this out. At least first try to understand the given conditions is the given conditions are indicating to something very well known we have learned in the previous session. So please tell me that what is that? Okay. I think that's important first. Okay. Please think about it and let me know. So are you able to figure out what it should be, or are you able to figure out that this thing is connected to what? Mustaq, can you please, Mustaq, please unmute yourself and let me know the answer. Okay, okay. It seems that it seems that it's you are not unable to figure out. So let me explain it. Okay. So first of all, so this condition is connected with the connectedness. Sorry. Hmm. So this is so-called a connectedness. Okay. This is first. So now the correct answer will be option two. That is close zero, close one. Okay. So why the other option will not possible? For option A, that is for R, we can take there exists obviously function f and g from R to R with f of R 0 comma infinity and g of R minus infinity comma 0. Okay, that is quite possible, right? That's not difficult. How? Damn, this is full R. Okay, this is the zero line. This is F. So what we're doing is that, so this is this and this one is 0 comma that one, and here we have this extra portion. We are putting that extra portion here. Okay, so the map will be x goes to x if x greater than equal to 0, and x will goes to minus x, that is x is less than equal to 0. That is the function will be what? X goes to mod x. Okay, so this will be our little f. Okay, and what will little g? And the little g would be what? So little g will be goes to minus mod x. Okay, minus 1. This will be g. Okay, so that will then, so this g will satisfy those properties. Okay, now for option 2, sorry, for option 3, hmm. So for option 3, that is what option 3 is consisting of. Option 3 is close 0, open 1. So define f from close 0, open 1 to close 0, open 1 with f of close 0, open 1 is equal to close 0, open half, and g of close 0, open 1 is equal to close half, open 1. And such a situation is always possible. Okay. So here the function will be x going to x by 2, and here the function will be x goes to 1 minus x by 2. Okay. And for why? So this says that option 2, option 1 and 3 are out of the race. And we need to show why option 3, for option 3, such a situation is possible. Okay. So option 2, 0, third bracket 0, 1. Okay. Now, if possible, let there exist continuous functions f and g. Okay, so if possible, there's continuous function f and g from close 0 and close 0, 1 such that f of 0, comma 1 union g of 0, comma 1 is equal to 0, comma 1 and f of 0, comma 1 intersection g of 0, comma 1 is equal to empty. Okay, so this is that. So this and of course, and also observe that image of f, image of g will only be of the form a comma b. So these situations, so all of this situation implies that 0 comma 1 can be written as a comma b union c comma d, and their intersection is empty. And of course, such a situation, obviously such a thing is not possible, right? Obviously, obviously not. Obviously, this is not possible. Okay, so that's why this option 2. That's why it's option 2. So option 2, correct option. Okay, so let me re-explain this. Okay, let me have some cup of water. Okay, so the question is as follows. Hmm. So uh, so suppose E is non-interceptor of R, and suppose there is two continuous function f and g from A to S, so that f union g is equal to f intersection g over m2. Now we need to show which one of the options are not possible for A. Okay. So firstly, the correct answer is only two. Okay, this is the first one. And the thing is that these two conditions in an intersection are corresponding with a connectedness only. Okay. Now let me give the argument. So suppose A is equal to R. If A is equal to R, then we know that for if G for two, so there exist two self maps on real and real line. Given one is x goes to mod x, another will be x goes to minus mod x minus one. So such a situation is always possible. That is, this satisfies the given condition. So yeah, so that is the problem. So that's why option one is possible. And what about option two? Option 3 is close 0 open 1. F and G are two maps from x goes to x by 2 and x goes to 1 minus mod x. Okay. And option 2 is close 0 comma 1. Now, if possible, there is continuous functions f and g 0 1 to 0 1. So f of 0 1 even g of 0 is 0 1. Okay. Now, image and g image of f will only be of the form close of third bracket ab. Okay. So this tells that one. So there is some issue with the software. Kindly hold a moment, please. Please please bear with me. 1 minute, please. Please hold a moment. Hmm. So now for option two, for option two, suppose suppose there are two continuous functions satisfy those property. Okay. Now since f is continuous and domain is connected, so image of f and image of b will be compact closed of the form this. Okay. So this tells what? This tells the closed 0 1 can be written as closed triple AB union closed triple CD. Now this is not possible. Why? Because as closed 0 1 is connected only. So such a situation is possible. That's why option two is only option, correct option. Okay. So yeah. So I hope. So is it clear to everybody? Is it clear? Okay, I hope so. So okay. So if it is not clear, please unmute yourself and let me know. Okay. Okay. So now let's move on the next question. 1 minute. Okay. So now let's move on to the next question. Okay. What happened? Uh, Question as follows that so consider the standard. Oh shit. Huh. So the question is consider the standard unit sphere S1 in the R2. Okay, Euclidean space. Then which are the correct? Then there exists a function f from S1 to R which is continuous and injective. Option 2. For every continuous function f from S1 to R, there exist uncountably many pairs of distinct points x and y in S1 such that fx is equal to fy. Okay. Option 3, image of every non-constant continuous functions f from S1 to R is a closed interval in R. So yeah. So now which one is correct? So let me read. So we have considered standard unit sphere in R2. Now firstly there is a continuous function f from S1 to R is a continuous inject, that is whether the circle can be embedded in real line or not. Second is there is a continuous function f S1 to R with uncountably many pairs of distinct point f x and y such that fx equal to f(y). The third is image of every non-constant continuous function f S1 to R is closed interval in R. Okay, think about it and let me know. Okay. So by the way, I must mention here is that more than one option may be correct. Okay. So please think about it, take your time, and let me know. Okay. Okay. So 1 minute. Okay. So, what's your opinion regarding which one will be correct or not? Okay. So, let me explain this. Okay. So first, let me tell you the what will be the correct answers. The correct answer will be, sorry, option two and option three. Okay. Now let me explain. Okay. So first, observe S1 connected, and even S1 minus a single point is connected. Okay. So f of, if such a function is exists there, so f of S1 minus single point, uh, mm, must be connected. Okay. Not only that, it will must be an, which will be an open interval, which will be an open interval in R. But S1 connected plus compact implies f of S1 is a closed interval of R, which is not possible. Okay, so that's a contradiction. So basically, if 2 points of S1, that is, if 2 points, that is, if 2 points of, that is, I mean, so, I mean, if it is injective, if injective, so if we remove 1 point from S1, so there 1 point S1 removed. So that f of this part, this removed part, suppose this part will go to there, okay? So then this part will must, so this point will go to there. So that will tell, so f of S1 minus singleton point, this has to be what? This has to be minus infinity, call it x, comma x third bracket, but that is not possible. Sorry, f of S1. But that is not possible, right? Due to compactness argument. Okay. Due to what? Due to connectedness. So yeah, so that is the argument. So that's it from, so that is S1 to R, there exists no injective function. So option one got kicked out from the scenario. Okay. Now let's option two. Option two is what? Option two is, so option one is kicked out. Now option two. Option two is, for every continuous function x, there are uncountably many pairs of distinct points x and y and h1 such that if x equal to fy. Okay. Now, as per the option one, try to figure out this option two by yourself. Take your time. Else I shall explain. Okay. Please think about for this option two for few moments that why it has to be true. Okay, think about it. Take your time. Okay. So are you able to so are you able to guess, Mustafa? Um, that option two, why it is correct? Option 2, why will be correct? Do you have any guess, Mustaq? Okay, so let me explain. Okay, for option 2, so in case if you have any doubt in between the session, please stop and ask me. Okay, so let if f of sorry, if f of 1 comma 0, this is equal to a, not equal to b, is equal to f of x comma y, for some x comma y not equal to 1 comma 0, then assuming a less than b, without loss of generality, we see that f inverse singleton x greater than equal to 2 for every x belongs to a to b. So the argument is that, so suppose we are assuming f of 1 comma 0 is equal to a, not for some x, okay? And assuming we are assuming a is less than equal to b, so this tells what? Mod of f inverse is greater than equal to for all x comma x belongs to a comma b. So that is the contradiction. Okay. So not the contrary. So that is, so that tells that there is in, so for so there are uncountable many pairs such that f of x equal to f of y. So that's all. And option three, why? Option three, what are the option three tells that image of every non-constant. What are the option three? Option three is what? Image of every non-constant continuous function f from s1 to r is closed interval in R. So option three is correct because s1 is compact plus connected. Okay, that's your option three is correct. Okay, so yeah, so that's all for this question. So I have this clear to everybody. There is nothing. So only we need to use the fact the x1 is compact candidate. So what will be the possible image after, even after removing one point? So you need to use the facts only. Okay, there is nothing extra I have used. So let's go for the next question. So let x be an uncountable set equipped with the discrete topology. Then x is first countable. Sorry, first countable, not second countable. Option 2. X is second countable, but not first countable. Option 3. X neither first countable, not second countable. Okay, so there are three options. So X is uncountable, so we got discrete topology. The topology is given to be highly discrete here. Discrete topology, then which topology? Either X is first countable, not second countable. Second must first countable. It is either not first countable, not second countable. Okay. So now you use the definition of first countability, second countability along with the discrete topology. Try to figure out the open sets and closed sets, and then you just only use the definitions. Only hint is only play definitions. Only play with definitions. Okay. Try to figure out and let me know. So it is nothing complicated. Only you use the definition and go along with that. You will get the answer automatically, I guess. Please take your time and think about it. Let me know. Okay. So, uh, so Mustaq, are you able to figure out this that which one will be correct or and why? So let me start with the recalling the different definitions. Okay. So firstly, there is discrete topology. So discrete topology means what? So by discrete topology, we mean singletons are open, singletons open. Okay, this is discrete topology. Okay. Second countable means it has a countable basis for its topology. Okay. A first countable means what? Each neighborhood, each neighborhood has countable basis. So this is what by first countable. Okay. Now, which one will correct? First, let me tell you the answer. I don't know whether are you able to guess properly. So let me tell you the answer. So answer will be option two. Okay. Now let me explain. Sorry, answer will be option one. Option. So let me explain. For all x belongs to x, the singleton x can be taken as countable neighborhood base at x. Okay. So this tells that x is first countable. Now since every singleton is open and x uncountable, and x is not second countable, which is quite obvious. So since singleton open, so singleton x can be chosen as countable neighbors. X is first countable, and why it's not second countable? Since every singleton is open and x is uncountable, so x cannot be second countable. Okay, why? Because if x is second countable, and let b be a basis of x, then for x each x belongs to bx subset of x. Okay, and what? And x is uncountable. There are uncountable many x, uncountable many x. So this implies bx uncountable. So this says that x cannot be second countable. Okay, so that is the argument. Okay, so it's not, so only you need to three pair. First one, x is discrete topology, singleton is open. Second is that second is that since x is uncountable, singleton is open and x uncountable, x is not countable. Okay. So this tells that the p tag is not countable. Okay, so that so tells it's not same models. Okay, so I hope this is clear. So now let's move on for the next question. The question is that which one of the following is true for infinite set? Which one is not true for infinite set X? Okay, answer is that if there are three options, every topology on X is still countable, then X is countable. Say option two, if tau is a topology on X, as that every subset of X with 10 elements is open, then X is first countable. Option 3, if tau is a topology on X such that every infinite subset of X is open, then X is first countable. So there are three options. First one was that um, if every topology on a set countable X is a countable set. If tau is a topology on X of every subset of X with 10 elements is open, the X is first count. And final option is tau is a topology on X, any infinite subset is open, then it's a first countable set. Okay. So so of course, yeah. So for this problem also you need to use the definition, so nothing more than that, and along with some tricks to solve the problem. Okay, so take your time, think about it, which one will be correct. So I shall not write the answer right now. Take your time, think about it. I shall be back within a few minutes. Okay, please try to solve it by yourself first. এই এই হ্যাঁ তো বললাম, তো বললো যে ঠিক আছে। তো বললাম যে 10 বলেছি তো কমিয়ে ওটা 9 করতে হবে তাকে। তো বললো, তো বললো যে হ্যাঁ ঠিক আছে। তারপর বললাম যে ঠিক আছে অ্যাডভান্স কত দিতে হবে, তো বললো যে অ্যাডভান্স তো নর্মালি 2 মাসে বলে, ওটা কমিয়ে 1 করতে হবে ওটাকে। রাজি হলো তো, তো রাজি হলো এটাই। তাহলে মার্কেটের মধ্যে দিয়ে ওকে নাম্বারটা দিয়ে দেবো তাহলে। খুব চাপ। এবার যদি বলে যে এবার এবার যদি হ্যাঁ এবার খাবে কোথায়, এটা আছে কোশ্চেন, ভাবছি। না না না, দেখ সে পরে দেখা যাবে, ফোন নাম্বারটা আমাকে পাঠিয়ে দেবে, পাঠিয়ে দেবো ওকে। না আগে নাম্বারটা পাঠাও কেন, আগে নাম্বারটা পাঠাবো, কথা বলুক তারপরেও, ওর কথা হয়ে যাক এর সাথে মালিকের, তারপরে ঘর দেখে আসার পর তারপর মালিককে বলবা যে নাম্বার দিয়ে দিয়ে আসা, এইভাবে বলবা। আগে থেকে যদি আগে ফোন কল বললা, তারপর তাহলে ফোন করলেন হতেই পারে, তাহলে সেটা সিচুয়েশন খারাপ হয়ে যাবে, তাই না? আগে ওর সাথে কথা বলে নি, তারপর তুমি বলবা যে এক দিন পরে हमने नंबर दे दिया था उसके बाद अपने बात के কিছু বল মাথার গুলো। আগে নাম আগে বলবা না, কিন্তু আগে নাম্বার দিয়ে দিলা, এর সাথে কথা বলো, তারপরে মালিককে বলবে যে আমরা দুদিন আগে নাম্বার দিয়েছিলাম, এরকম করে বলবা। মাথার গুলো। না না সে তো, না না সেটা নিয়ে সমস্যা নাই তোমার, এখনই মালিককে জানার কি আছে যে ফোন করবে, এই কথা এখনই জানার আছে কথা, যদি ফোন না করে, সেই জন্য কথা বলছি। খুবই চাপ, আসলে কোনোদিন বাইরে থাকিনি, কেমন লাগছে বাইরে। কে? হ্যাঁ সব আছে। যাই না, যাই না। পোস্ট ডক করছে কেন? দ্যাট পিএইচডি করার সময় আসবে, তাও মানে পোস্ট ডক করার সময় কেন আসবে? হ্যাঁ, সে পেতে পারি, সে পাই অলরেডি আমি। না, তারপর অনেক অ্যাপ ফ্যাপেও ঘর বাড়ি পাওয়া যায়, এবার ওর কাছে স্মার্টফোন নেই, নর্মাল সুইচ টিপা ফোন, ল্যাপটপও নেই। তো একটা জিনিস, ফোনের চার্জার কিনতে হবে, তো বললো অ্যামাজন ইউজ করেনি কোনোদিন। দিয়ে দেবো, কোনোদিনই ইউজ করেনি। মানে ব্যাপারটা যে যেহেতু একদিন হোস্টেলে ছিল, ওই কারণে অন্য কাউকে বলতো, অর্ডার করে দিত, নিজে কোনোদিনই কিছু করেনি। এবার বুঝলাম বাইরে কেন যায়নি, এবার মাথায় ঢুকে গেছে, বাইরে গেলে হারিয়ে যাবে তো, চাপ আছে। হ্যাঁ, ইংলিশ তো বলা উচিত। আরে তোমাকে বলার কি আছে, অত দিতে হবে না। আরে তোমার বলার কি আছে, অত দিতে, এটা কথা হলো নাকি? बोलो जे वो 9,000 देने के लिए राजी है और 1 मास का एडवांस देने के लिए राजी है, तो आपका नंबर उसको दे रहा होगा, बोलो। है? हाँ, তুমি বসে বসে গেস করো। না না, সেটা সমস্যা কথা নয়, আমার সেটা নিয়ে সমস্যা নাকি, তুমি কাজটা করে দেখাও। কথাটা হচ্ছে এটাই। Okay, so okay, so Mustaq, are you able to figure out what will be the proper answer or any guess? Okay, so let me write down the answer. The point is that one option, the three options are correct. All are correct. Okay, the first thing. Okay, now for option one, note that uncountable set with a discrete topology is not second countable. And option for option 2 and 3, for option 2 and 3, the given condition implies that every singleton is open. So this is actually very short way. So think about it why, okay? So option 1 is clear, there is nothing to explain. And for option 3, for option 3 and 2 and 3, so given condition tells every singleton open, okay? Why? Okay, think about it. So I shall not explain this. Think about it. Okay. This is not difficult. This is very easy. So that's why I am leaving it. So now go for the next question. Let x and y be spaces and f X to a continuous map. Then if is injective, option 2. Sorry, if is injective, y is second countable, if f is injective, y is second countable, then x second countable. Okay. Option 2. If f open, surjective map, and y is second countable, then implies x second countable. Okay. Third option is if f open, surjective, and x second countable, then y is second countable. Okay. So these are the three options. So basically, what is the question is that x and y such if it's a continuous map, and if it's injective, y is second countable, the x is second countable. If is open surjective, y is second countable, the x is second countable. And third is if f is open surjective and second countable, then y is second countable. Okay. So there are three options. Try to think which one will be correct and which will not. Okay. So only here we would use the fact the continuous map send for open continuous map send first countable, send second countable. All these facts you need to use somehow for this. So think about it and let me know. So I shall be back in a few minutes. Okay, take your time. Okay, কি বলছিলাম? হ্যাঁ সেটা সম্ভাবনা রয়েছে। হ্যাঁ এই ব্যক্তি এরকম আছে। আর সেটা একটা না পাওয়া গেলেও অনেকটা কাছাকাছি পাওয়া যাবে। দেখ যশস্বী ব্যক্তির গাইডও হতে পারে, ঠিক আছে? গাইডও যশস্বী ব্যক্তির মধ্যেই পড়ে। কি? এটা হ্যাঁ এটা গাইডও হতে পারে। এটা ব্যাপারটা না। এমনি হেল্প করতে কোনো সমস্যা নেই ওখানে। দেখ কি বললো কি পারলুম ফোন নাম্বার দিব কি দিব না ওকে? ও, Okay, so 1 minute. Okay, so the answer. So let me know the answer first. Okay, the answer will be only option three. Okay, so for one, if we take for why the option one is not correct, because if we take x equal to y is equal to real line or any uncountable set. Okay, and f is equal to identity. Okay, and take and equip x with discrete topology. Okay, and y with indiscrete topology. So, so basically we are choosing the spaces x and y are same as a set, but the topology which we are giving on x and y different. On x, on domains that we're giving discrete topology. On codomains, we're giving indiscrete topology. Okay. So now, so the identity map from x discrete to x indiscrete. It is, this is anyway injective, of course, injective, but x with discrete topology is not second countable. Why discrete topology is second countable? Okay, so that's why option one. So that's why option. So that's why option one is not um correct. So that's why option one is out of the picture. Okay. Now for option two, um, for option two, take x. Option two take x to be a non-second countable space, and y as a singleton. Okay. So in that case, any map f from x to singleton. This must be open, and of course surjective. Correct. 1 minute. Let me. There is a problem in the software itself. Let me. 1 minute. Please hold a moment. So X is open and surjective, okay? This open and surjective plus, of course, this one is second countable. Codomain is second countable. There is nothing confusing, but the domain is not second countable by choice. Domain is not second countable by choice. Okay. So that's why option 2 is out of the picture. And only option 3 left. How to prove it? For option 3, we need to show what? If is open surjective and X countable. Option 3, what to show? To show if open, if if open plus surjective and X second countable, then Y second countable. Okay. And we have already seen that now and this is true. Why this is true? Because this is true as if U is a countable basis for X, then f of U forms a countable base for Y. And this is already done in class. Already proved in previous sessions. Okay. So so now so there is one last question for today. So the question is that let X be an uncountable set, show that every subset of X with cofinite topology is compact. X uncountable set show that every subset of X cofinite topology is compact. Okay. So every okay. This part we have already seen. For the next part, and show that every subset of X with co-countable topology is Lindelof. Every subset of X with co-countable topology is Lindelof. Okay. So the first part already done. Now we are considering for the second part only, okay? So think about, so try the second part. So co-coordinate topology is always length up, okay? So what we will do, so choose an open cover, let U alpha be an open cover, okay? And let X belongs to U alpha, okay? So X minus U alpha naught is a countable set. Call these points will be x1, x2, xn dot dot dot. And then xi will belongs to u alpha I for some. So we can write x equal to u alpha naught, u alpha 1 dot dot dot, u alpha n dot dot dot. So that's what we can write, x equal to union of u alpha I is equal to 0 to infinity. So this tells that x is Lindelof. 1 minute. So yeah, so that is the argument. So we have done basically nothing extra. What do we choose? We choose first some open cover of x. We choose some open cover of x and we choose some fixed point. This will belong to some u alpha naught. And since co-coordinate topology, so complementary u alpha naught will be a countable set x1 is to xn and so xi belongs to u alpha I. Okay. So this tells that x equal to union of u alpha and this tells that x is lambda alpha. Okay. So yeah, so that is the argument. So yeah, so one- okay, so that's all for today. We shall meet on tomorrow from 7 to 9. Sorry, we meet on tomorrow from 7 to 8. It will be a 1 hour session, and upcoming Sunday will be the last session from 7 a. So from 7 to 9, 2 hours. Okay. So today I'm leaving the session. If you have any doubt or any question, please ask me in the next session. You can drop an email. Okay. So I'm leaving the session. Thank you.